Hey everyone, and welcome back. On behalf of Forge College, I am absolutely pumped to dive into today's explainer with you. Now, in our last session, state and storage mechanics, we poked around under the hood to see how data actually lives on the blockchain without, completely imploding. But today, we're zooming out. We're looking at the whole factory floor. We're talking architectural differences and runtime constraints. Basically, we're going to figure out exactly why the blockchain loves to look at your perfectly good code and say, yeah, absolutely not.
Here is our blueprint for today. We'll start off with the constrained workshop, then weigh throughput versus latency, dig into resource accounting, look at some real-world failure modes, and finally wrap it all up with your migration blueprint. All right, part 1, the constrained workshop. I want you to picture the blockchain runtime as a workshop. But, okay, this isn't some chill weekend hobby garage where you can just take your time. No, this is a heavily shared, deeply constrained workshop run by a terrifyingly strict manager holding a literal stopwatch. In this setup, your smart contract transactions are the artisans. They show up to work bringing tools, which is your compute, and materials, which is your state, all to hammer out some brand new state. But that manager, they're watching everything. They strictly regulate every millisecond you're on the floor, the exact tools you can check out, and they obsessively audit the ledger just to keep the whole place from descending into total chaos. To manage that chaos, every single blockchain architecture enforces 3 unbreakable rules. First up is capacity. This is the hard ceiling on the amount of compute the runtime can sweat out in a given second. Then there's predictability. This means if an artisan uses the exact same tools and materials today, they better produce the exact same piece tomorrow. No weird surprises allowed, period. And finally, isolation. This is basically making sure that if one artisan accidentally drops a 50-pound anvil on their foot, it doesn't ruin the masterpiece of the artisan working at the next bench over. It's these 3 rules that are going to completely dictate the boundaries of what you can and cannot build. Moving right along to section 2, throughput versus latency. Now this is where the workshop has to balance churning out massive volumes of work against the raw speed of individual tasks. And you can't just magically crank all the dials to max. Physics still applies here. On one hand, you've got batched work. This is where the manager lets a huge crowd of artisans do their thing all at once before finally locking the ledger. The upside? Massive throughput. The downside? Painfully slow latency for each individual transaction. On the flip side, we have short slots. Here, the manager is checking the ledger constantly. You get incredibly snappy, lightning-fast transactions, but boy, does it put massive pressure on the system to propagate that state instantly. As you'll see, these trade-offs literally dictate your architecture. If your target chain runs on short slot times like we see in SVM architectures like Solana, you get that ultra-low latency, but you absolutely have to prep your code to handle aggressive pipelining and rapid-fire writes. Conversely, large block times, like you'd see in the EVM, give you high throughput for batched work, but your users are going to be sitting around twiddling their thumbs waiting for confirmation. Plus, if the chain meters every single instruction, you can scale beautifully in parallel, but any heavy, unoptimized operations you've got are going to get bogged down super fast. Let's roll into section 3, resource accounting rules. Okay, this is where abstract theory hits your wallet like a freight train. Let's compare an older EVM-style architecture with the newer SVM approach. The EVM uses a pretty coarse gas model. The hidden trap here? Heavy storage writes can cause these nasty I/O bottlenecks at the node level that you honestly won't even see coming until things grind to a halt. The SVM, on the other hand, does not play around. It demands explicit compute unit budgets, and it forces you to declare exactly which accounts you're touching up front before you do anything, just so it can parallelize the work. Basically, if you're transitioning from EVM to SVM, you can't just wing it anymore. You have to declare your tools at the door. Which brings us to section 4, real-world failure modes. I want you to imagine the clumsy artisan. They just go waltzing into the workshop carrying this massive, monolithic transaction, trying to update 3 different accounts and write a giant storage summary all at exactly the same time. Now, on an EVM chain, this giant, clumsy block of logic might slowly, eventually squeeze its way through the door. But on an SVM, with its strict compute budgets and parallel scheduling, oh, no way. It crashes headfirst into a compute limit, fails the account declaration check, and gets instantly tossed out into the alley by our strict manager. So how do we fix this spectacular failure? You have to abandon that monolithic approach entirely and lean into safe recovery patterns. First up, idempotent checkpoints. Now, idempotent is just a fancy engineering word that basically means you can smash the button 10 times, but it's only going to charge you once. It's repeatable without side effects. You also want to use explicit 2-phase commits, and most importantly, you've got to persist your intermediate state. You need to save your progress so you can safely recover when one of those steps inevitably blows up in your face. All right, let's wrap this up with Section 5, your migration blueprint. If you're looking to successfully migrate your code between these wildly different architectures, here are your 3 vital steps. Step 1, decompose those massive, clumsy, monolithic transactions into smaller, bite-sized, composable pieces. Step 2, add idempotency keys to every single step so that your retries don't accidentally duplicate your logic. And step 3, implement intermediate state checkpoints so you're always saving your progress along the way.
If you take absolutely nothing else away from the source material we've covered today, please remember this quote: "Design for the workshop, not the artisan." You absolutely must align your transaction patterns to the specific metering, scheduling, and constraints of your target runtime. You can't force a platform to adapt to your code, right? Your code has to adapt to the platform.
To actually put that into practice, use this migration checklist. Map out every single expensive operation in your current code to the new target's specific metering rules. Don't just test the happy path. Simulate your absolute worst-case compute and I/O execution. And finally, make observability a first-class concern. You need to instrument your tests to specifically hunt for chain reorgs and partial failures, so you catch any weird state divergence way before you ever hit a production environment. As we close out this explainer, I want to leave you with one final question to chew on. Are your transactions genuinely ready for explicit compute unit budgets and parallel execution? Take a long, hard look at your code today. Well, on behalf of Forge College, thank you so much for hanging out with me. Be sure to check out our website at forge.college to learn more about this subject, dive deeper into all things Web3, and get yourself prepped for our very next lesson on execution models. Keep learning, keep building, and I'll catch you in the next one.